Have you ever stopped and wondered why some things just happen? And more importantly, why they never seem to happen in reverse? Well, today we're going to pull back the curtain on one of the most fundamental laws in the entire universe. It's a concept that dictates everything from your morning coffee to the ultimate fate of the cosmos. We are going to finally understand entropy.
Seriously, think about it. You pour cream into your coffee, give it a stir, and poof, it's perfectly mixed. But have you ever seen that coffee spontaneously separate back out, with all the cream gathering into a neat little blob? No way. Or how about a scrambled egg unscrambling itself in the pan? Of course not. These things just don't happen. The real question is, why?
Well, it turns out the universe basically has a preferred direction for how things play out. It's like a cosmic one-way street for everything. And the secret traffic cop enforcing this rule, the fundamental law behind it all, has a name: entropy.
So let's dive right into this idea of a one-way street. We're going to explore why heat naturally flows from your hot coffee into a cold room, but you'll never ever see a cold room spontaneously make your coffee hotter.
So how do we wrap our heads around this? Okay, here's the key. You have to forget everything you've ever heard about entropy being disorder or chaos. Just for now, let's toss that idea out. Because at its heart, entropy isn't about messiness. It's just a simple game of chance. It's all about probability.
To see what I mean, let's imagine a super simple setup. Picture 4 little particles, and they can be in one of 2 identical boxes, a left box and a right box. That's it. That's the whole game. And believe it or not, this little model is going to unlock the whole concept for us. All right, so how many different ways can we possibly arrange these 4 particles in our 2 boxes? Well, each particle has 2 choices, right? Left or right. So that's just 2 times 2 times 2 times 2, which gives us 16 totally unique arrangements. And each one of these specific layouts has a name. We call it a microstate.
But here's where it gets really, really interesting. We can group these 16 microstates by how the particles are distributed overall. For instance, there's only one way to have all 4 particles crammed into the left box. But look at the even split, 2 particles in each box. There are actually 6 completely different ways to get that same outcome.
And this is where the light bulb goes on. It's all about probability. If you just check on this system at some random moment, there's only a tiny 1 in 16 chance you'll find them all on one side. But there's a much bigger 6 in 16 chance, that's 37.5%, that you'll find them evenly split. The most spread out arrangement is just flat out the most likely. Why? Simply because there are more ways for it to happen.
So here's the absolute knockout punch. The universe doesn't have some weird mystical force pushing things toward disorder. It's just playing the odds, constantly. The state that has the most possible arrangements, the most microstates, is simply the most probable one. And that, right there, is the state with the greatest entropy. It's that simple.
Okay, so we've got the core intuition down. More ways equals more probable. Now let's see how we scale this simple idea up from our little 2-box game into a full-blown universal law, complete with the actual equations that scientists use.
You know, this idea didn't just appear out of nowhere. It was built up over decades. It started with Sadi Carnot thinking about steam engines, then Rudolf Clausius gave it the name entropy, and finally the absolute genius Ludwig Boltzmann was the one who connected it all to the probability of microstates, exactly what we just did with our boxes. So let's just make sure we've got the official language down. That term microstate, which scientists label with a W, is just one of those 16 specific arrangements we counted. It's like a perfect snapshot of exactly where every particle is and how much energy it has at a single instant. And this brings us to Boltzmann's legendary equation for entropy, S. Now I know equations can look a little scary, but the idea here is incredibly simple. That K is just a number to make the units work out, and the ln is just a math tool to handle the insanely huge numbers you get in the real world. The only thing you really need to see is this. When W, the number of microstates, goes up, S, the entropy, also goes up. That's it. More possibilities means higher entropy. Awesome. So now that we have the formal definition, let's get out of the land of theoretical boxes and see how this plays out with actual stuff, with real matter and energy all around us. A perfect place to start is with the states of matter. Think about a solid, like an ice cube. Its atoms are locked into a neat crystal grid. They can jiggle around, but that's about it. There are very few ways to arrange them, so low entropy. But what happens when you melt it? In a liquid, the particles can slide all over each other. Way more arrangements are possible, so you get higher entropy. And a gas? Oh man, in a gas, they are flying everywhere, filling up whatever container you put them in. The number of possible locations is astronomical. That is the state of highest entropy.
And temperature is a huge piece of this puzzle too. When you heat something up, you're not just making its particles move faster, you're also spreading out the range of their energies. The energy becomes more dispersed across all the particles, which means there are more ways for that energy to be arranged. So here's a simple rule. Higher temperature always means higher entropy. All right, now for the really fun part. We can actually use what we've learned to predict whether entropy is going to go up or down in real-life situations. So, you think you're ready? Let's put our new knowledge to the test.
Okay, first question. You take a crystal of table salt, a really ordered, structured solid, and you drop it into a glass of water where it dissolves. What happens to the entropy of that system? Does it go up or does it go down?
It increases. Absolutely. Think about it. Those salt ions were trapped in a rigid structure, but now they're free to roam all throughout the water. The matter has spread out, the number of places they could be has just skyrocketed, and so the number of microstates, and therefore the entropy, has gone way, way up.
Okay, you ready for another one? Let's flip it around. What happens to entropy when you take that free-flowing liquid water and it freezes into a highly structured, solid block of ice? You got it. It decreases. The water molecules lose all that freedom they had. They go from being able to be pretty much anywhere in the liquid to being locked into fixed positions in a crystal. We've just massively cut down on the number of possible arrangements, which means we've lowered the number of microstates, so the entropy of the water goes down.
So you can probably see the general pattern here. Entropy, which scientists often write as delta S, goes up whenever things melt, or boil, or get hotter, or dissolve. The basic rule is this. Anytime matter or energy gets more spread out, entropy increases. And it makes sense that it would decrease for all the opposite processes.
So look, if you take only one thing away today, let it be this. Please stop thinking of entropy as disorder. A much better, much more accurate way to think about it is as a measure of dispersal. It's simply a way of counting all the possible ways that matter and energy can be distributed or spread out in a system.
And that leaves us with one last kind of mind-blowing thought. The second law of thermodynamics says that the total entropy of the entire universe can only go up. It never goes down. Everything that happens everywhere is pushing the cosmos toward a state with more possible microstates, a more probable, more spread out future. Which leads to a really profound question. If everything is constantly and irreversibly moving towards maximum dispersal, what does that mean for the ultimate fate of the universe itself?